In this example, we're going to cover whether or not this sequence on the left-hand side converges or diverges. Now remember, when we're thinking about sequences, sequences are infinite lists of numbers. And when we talk about the convergence or divergence of a sequence, when a sequence converges, what this means kind of intuitively, at least to me, is when we go out really, really far down that list, all the numbers start looking identical. As in the sequence converges to the same thing if we keep going further and further out. All the numbers look identical really far down that list. So that's kind of what I intuitively think about for sequences, which is why when we approach convergence and divergence, we take a limit to ask, what do those terms really far out look like? All right, well, let's go ahead and actually go with this problem. So this is the sequence that we have of cosine, the quantity n squared pi, all divided by the quantity n squared plus 5. So in this particular problem, all of the n dependence is inside of the cosine. So the terms in the sequence are changing by what's inside of the cosine, as in there are no n terms outside of that cosine anywhere. So when we think about taking the limit here, asking ourselves, what do the terms really far out in the sequence look like? Well, inside of that cosine is where all the n's are changing. So this limit actually really only affects what's inside of that cosine function for us. So when we think about taking this limit, we only really have to worry about, well, what's inside of this cosine? Or we can think about this as we take the limit of what's inside the cosine, the n squared pi over n squared plus 5, and whatever that limit comes out to be, we take the cosine of it at the end of the day. So let's take a look at what this limit looks like as n goes to infinity. Well, inside of that cosine, the n squared pi in the numerator as n goes to infinity. This thing looks like it's going to infinity in the numerator. In the denominator, we have that n squared plus 5, and as n goes to infinity, this denominator also looks like it's going to infinity, similar to the numerator. So because of this, we get to do a L'Hopital's rule. So again, we're thinking about just whatever this limit comes out to, we take the cosine of it at the end of the day. So the limit is inside of the cosine, the way we're thinking about it, and we can do a L'Hopital's rule. So taking the derivative of the numerator, taking the derivative of the denominator separately, and reevaluating that limit. So the derivative of the numerator with respect to n is 2n pi. In the denominator, that limit is, well, a2n. So again, from this second line to this third line, we did a nice L'Hopital's rule. All right, so now let's reevaluate what we have here. And before we proceed any further with this limit, well, we can see we're going to get some cancellations. The two n's cancel out in the numerator and denominator. So really what we have left over here in this problem is we have the cosine of the limit as n goes to infinity of just the number pi. So since pi by itself has no n dependence, that limit as n goes to infinity of pi, well, that thing's just equal to pi. So what this limit looks like as n goes to infinity is simply cosine of pi, which is a nice constant for us. It's equal to -1. So the terms really far out in the sequence all begin looking like -1 the further and further we go. So we would say that the sequence converges to -1.